Okay, so last time we talked about just like basic probability practices. This time we're going to talk about some other things that can occur. So, for instance, probability of the union. That's supposed to be an N. Of two events. Okay. So when we talk about this, it is written as if A and B are events in the same sample space, the probability of A or B occurring is given by the probability of A union B, which is equal to the probability of A plus the probability of B minus the probability of A intersects B. And we'll talk about this stuff in a second. So if you're not familiar with like Venn diagram notation, this will make more sense momentarily. Um, if A and B are mutually I don't know if you guys can hear my kids in the background, but I'm sorry.
I can't. They screaming.
They're going crazy, dude.
Do you need me to tell them to stop talking?
No, I'm about to. Don't worry. I'm about to go out there and be like, what are you doing?
I can always do it if you need me to.
Probability of A.
Nick, if you do it, they'll start crying.
Dude, no, Luke likes
make
it.
his kids cry. Make his kids cry.
It'll
scare them.
That's okay. So that's our rules for this. Where if A and B are mutually exclusive, then the probability of A union B is just the addition. The probability of A or B occurring. So this one's like an or statement. This is mutually exclusive, and we'll talk about some problems here in a second. I just want to make sure everybody has a second to write that down.
What does mutually exclusive mean?
We're getting there, bud.
That's cool.
I need to think about how I want to word that to you.
They can't happen at the same time.
Yeah, I know. But like,
thank you, Jackson.
Yeah. No outcomes in common. There we go. So they're like they don't share anything. If that makes sense.
Not even a little.
Wow. All right. Cool. Well, you're a lost cause. Okay. I can't help you. No, like basically, like if you have two different events happening, then mutually exclusive means they can't share anything. They're separated from one another. Like there's no overlap of the events.
It's like a stoplight can't be red and yellow at the same time.
I mean, it can if it malfunctions.
Well, that's
if you turn two lights
that's
on,
college. That's college stats.
All right, so let's look at one card is selected from a standard deck of 52 playing cards.
I feel like we've done this exact same problem like a million times over the past 2 weeks. Well, that's okay.
What is the probability that the card is either a heart or a face card?
Oh, those overlap. Okay, yeah.
Yeah. Now you get the difference. Yeah.
Okay.
Okay. Because we have to pay attention to this or. Like they overlap. So they share something in common, right? So like this is one of those instances where you go based off the or statement, which means I need the probability of a heart, which is going to be 13 over 52. But I need the probability of a face card. Well, the probability of face card is 12 over 52. But then you need to find the probability of heart intersects face card. What this really means is it's a heart and a face card. All right. Wow, that just erased right out of my card. All right, thank you. So if it's a heart and a face card, there's only 3 of those out of the 52, right? Jack, king, queen of hearts. So now you have everything you need, where you need to go through and you need to remember you're doing the probability of a heart plus the probability of a face card minus the probability of both. Just because I don't have enough room to write heart and face card. All right, so you're going to do 13 over 52 plus 12 over 52 minus 3 over 52. Good news, they all have 52 in the denominator, so you don't have to find a common denominator. You just have to add and subtract. 13 plus 12, 22, minus 3, 19. 19 out of 52. $22. Why did I do that? I even said it. 25, 22. 22.
That's tough.
Yeah. Okay. So that's one of those instances that it's an or statement. Are we okay with that? Does that make sense to everybody?
Yep.
Okay. I'm going to find a better mutual exclusive example that I have as far as like a word problem with one, because the one that I have currently is not good.
Bro, we gotta start using something other than cards.
I mean, but cards are so much fun, dude.
Can we use like a bag of marbles or something?
Yeah, dude, I got you. Don't worry.
Let's go. Well,
not,
like I don't know.
It's not gonna be marbles, but I got you. Don't worry.
I don't know like how many of each thing a deck of cards has.
Yeah, Nick needs like colors, like bright objects.
You mean how I wrote it out for you and I left it on the notes for that probability on Classroom?
We don't look at those.
Wow.
Come on,
All right,
you can literally look it up. You can look up how many cards are in the deck.
Google doesn't exist. What do you mean?
Look up? No. You should just.
I know that's 52. I'm saying like whenever he's like, there's this many hearts, this many this many that. Like I don't know. I don't care. I'm not a magician.
Just count, bro. Count. It's 1 through 10, and then 3 extra. Just count.
All right, this is independent events, and don't worry, I'm gonna write out the definition of independent in just a second too. If A and B are independent events, the probability that both A and B will occur is given by the probability of A and B equals the probability of A times the probability of B.
Let's go.
Wild.
Okay, John, this is for you, man. 2 events are independent if the occurrence of one has no effect on the occurrence of the other.
Okay.
Okay. All right, Nick said he wants something that isn't cards. So
Let's go.
a random number generator.
Oh my god.
That's more boring. Like, just
On a computer. Selects 3 integers.
is this computer programmed to not repeat a number or?
You're about to find out, dude.
Okay, I'm so sorry.
Actually, don't tell you, so no, it's not. It just lets you know that it'll select a number between 1 and 20, but it doesn't tell you anything other than that. So like it could repeat. What is the probability? That all 3 numbers are less than or equal to 5. Well, we know the probability of selecting the number 1 through 5, right? So, probability of selecting 1 through 5. Well, there's 5 outcomes, right? 1, 2, 3, 4, and 5. Out of how many numbers?
20. It's 20.
20. Which gives you 1/4. All right, we're selecting 3 times because they're independent of each other. They don't matter. So you're going to take the probability of that event A. So probability of 1 through 5 times the probability of 1 through 5 times the probability of 1 through 5. Well, that's 1/4 times 1/4 times 1/4, which is 1/64.
Wow.
So there's a 1 in 64 chance that happens.
Hey, that was my football number.
That's why.
All right. So far, so good.
Yes, sir.
Okay, so now we have... Okay, I'm going to write this part out because this is probably new to you. The complement of an event. Is the collection of all outcomes in the sample space that are not in A. All right, so the probability of a complement we're going to let A be an event and let a complement be its complement. If the probability of A is P of A, then the probability of the complement is given by 1 minus the probability of A. So basically, it's everything that didn't occur. So if we go back and we think about our previous example, well, it's 1 out of a 60. Like it's just the probability of something that it can't occur. All right, and I'll do an example of this on Thursday. I'm gonna stop right there for today on that part. That way we can continue on Thursday with more probability.